Welcome back, everyone. In part 2 of k-means clustering for color quantization, we're going to actually code through the process we just described in part 1. Let's get to it by heading over to a Jupyter Notebook. Okay, here I am at a brand new notebook, and we're going to import a couple of libraries that we haven't actually used yet. So obviously we've used NumPy before, but we're also going to import Matplotlib, and we're going to import pyplot as PLT. So recall, this is the plotting portion of the Matplotlib library, by far the most popular aspect of Matplotlib, but Matplotlib also has an image processing library within it. So we're also going to say matplotlib.image, and we're going to import this as mpimg, basically matplotlib image, and this has some useful functions that can directly read in JPEG and PNG files and convert them into NumPy arrays. Because keep in mind, when we're talking about images, we're talking about file extensions like JPG or PNG, etc. And we need to end up converting these to a NumPy array. And that's what the matplotlib.image library allows us to do. So what we're going to say here is mpimg imread. And this is a function within matplotlib image that allows us to read in direct images like JPEGs and PNGs and convert them directly into NumPy arrays. And inside the data folder, so I'm going to go back up one directory to data, there is a file called palmtrees.jpg. You should be able to tab autocomplete that. And then we're going to say, if you just run this, it returns back the array format of JPEG. So what we're going to say here is image as array is equal to mpimg image read.jpg. And you can technically do this for any image you have on your computer. In fact, I would encourage you to play around with this and see color quantization on other images beyond the palm tree image we showed here. The reason we showed the palm tree image is because it has a very clear gradient with many colors that is going to really clearly show the effect of quantization at the end. So we have this image as an array. So here we can see image as array. And essentially what you're seeing here are three sets of brackets. Note that denotes that this is a three-dimensional object. So if I check the shape of this array, it has a height of 1,401 pixels, a width of 934 pixels, and then 3 color channels. So again, recall that the way NumPy works along with Matplotlib is this is height, width, and then color channels. So there's 3 color channels, red, green, blue, 934 pixels in width, and then 1,401 pixels in height. So that is our image as an array. And if we take a look at it again, image as array, note here that this is essentially 1 pixel value for red, green, and blue. And you'll note that it's kind of repeated because these 2 pixels right next to each other are the exact same color. So we have our image now read in as an array. We can display it now with Matplotlib. So I can say plt.imshow, pass in the image as array, run that, and that will actually programmatically display this image here in Jupyter. Keep in mind, this is kind of a blurry version of the image. You can always, depending on how many pixels the image has, you can say plt figure and then choose some higher dimension. So you can say DPI is equal to 200 or something like that, run that, and it's going to expand the size of the image in order to show you more clarity there. So keep in mind, since we're dealing with a real image that has pixels, you're going to be possibly stretching this out depending on what figure size you choose to display here. But main idea is that imshow can display in NumPy array, and in this case, it's going to appear as an image. And note how Matplotlib automatically knows what colors or what channel is red, what channel is green, what channel is blue, because as we keep mentioning, that's pretty much standardized here for Matplotlib and NumPy. What you would not be able to do is pass in this JPEG file path into plt_imshow. plt_imshow needs the NumPy array. It does not actually show you a JPEG file or a PNG file. That's why we have this extra step in order to display the image. So now let's use k-means to quantize the colors. What we're going to do here first is recall we right now have a three-dimensional array that is in something like height, width, and then color channels. And we need to convert this to be two-dimensional as we previously discussed. So essentially we need to convert this to look like something like height times width, comma, colors. So let's go ahead and do that. What we can do here is I can directly tuple and pack that shape. So if I say image as array dot shape, recall it returns back this tuple. So I'm just going to assign this to height, width, and color. Essentially, right now all I'm doing is I'm making 3 new variables, h, w, and c, and I'm going to assign them to each separately. So now if I call h, I get back the height. If I call back w, I get back the width. And if I call c, I get back that there are 3 color channels. So then I'm going to say image as 2D array, or let's go ahead and say as array 2D, so we match the notes. That's equal to image as array, and then I'm going to reshape it. So again, we're reshaping it from 3 dimensions to 2 dimensions by now saying go ahead and reshape this as height times width on the first one, essentially flattening out each color channel, and then just saying each column is going to be equal to a color channel. So 1 column for red, 1 column for blue, and 1 column for green. So now all the rows are essentially all the pixels in a single color channel. And now we have image as array 2D, and it's essentially reformatted. So now that it's in 2 dimensions. If you take a look at image as array, note here that it looks kind of similar, except the number of braces or brackets is different. So this denotes that this is 3D, and you can check with length. So this has, whoops, we can check the length of shape, excuse me. So check the length of shape, and it'll recall that this is a 3-dimensional array. And if we copy this and say image as array 2D and check the shape there, this is now 2 dimensions. All right, so make sure you take a look at the previous video for a further discussion on how this flattening out is actually working, but you get the idea. We're reshaping from 3 dimensions to 2 dimensions, just rearranging the actual values in the array itself. Now we're ready to perform k-means clustering. So we'll say from scikit-learn.cluster import k-means. All right, now what we're going to do is create an instance of our model. We're going to say model is equal to k-means with number of clusters, and let's say number of clusters is 6. This is essentially saying I want to quantize this down to 6 kind of averaged out colors. So we say labels is equal to model, and I call fit_predict, which will return back those labels, and I'm passing in image as array 2D. I can't pass in the 3-dimensional array because k-means needs it in a 2-dimensional format. So we run that. That's going to take a little bit of time to fit. The larger the image, the more time it's going to take to fit, because keep in mind, right now, we have 1,401 times whatever the width was. So if we scroll back up here, we can see the width, which is over 750. It's 934. So we're going to say come back here to 934. So we have almost 1 million data points here. So sometimes you may want to just take a small sampling of the photo to do the actual k-means clustering, because this image can cause a lot of data points. But we're done training, so that wasn't too bad. We have model.fit_predict. Now if I check out my labels, it's 0, 1, etc. And there should be kind of up to 6 values. So 0, 1, 2, 3, 4, 5. Those are my actual labels. And as I keep mentioning, you may get different numbers here, but for the most part, your first 3 numbers should be the same, and your last 3 numbers should be the same. So as we previously mentioned when we talked about k-means clustering, these numbers themselves are kind of meaningless. What actually is important is the fact that the points belong to the same cluster. Whether that cluster is a 0, 1, 3, 4, etc. doesn't actually matter. So we've already discussed that in our first discussion of k-means clustering. And what we really want to know is what are the cluster centers? So we can actually grab this by saying model dot, and you'll see clusters underscore centers underscore, and this returns the cluster centers themselves. So what is this? These are essentially the 6th averaged out red, green, blue values. And there's a lot of decimal points here, so let's go ahead and round this out. So in order to convert these into RGB color codes, we want them as integers. So I'm going to say my RGB codes are equal to these cluster centers, where the first column is red, second column is green, third column is blue, but I want to round it to 0 past the decimal. And then I'm also going to say as type integer. So we can do this all in one step there. So we can say RGB codes, and it's going to be the same values, so just round it off so that they're integers. That way we don't have any display issues here, because you technically don't really choose a value of red as 72.3345, etc. Instead, you just want it as kind of this whole integer value. Note that one of these values is very low across all channels, indicating this is probably very close to black. So it found the center for those shadowed palm trees here. It's basically, there are some dark grays or very dark colors, but it's just going to say, okay, if you're dark enough here, they're all going to be shown as black. So let's check this out. What we need to do is assign these RGB color codes. So how do we actually do this? Well, if we have the RGB codes and I have labels, so recall that I have here labels, then I know that my labels array is associated with these RGB codes. So label at 0 is this color. Keep in mind, this may appear in a different order to you because we didn't set a random state, and K-means clustering has a random starting point. But somewhere in your red, green, blue color codes, you should probably see a color that looks very similar to something like 3, 3, 4. Now, it may be the first row, maybe the second row, etc. But you'll notice here that I'm matching up 0 with this particular color center. So that means this cluster of 0 has essentially this RGB code assignment to it. So what I'm going to say is RGB codes and pass in labels. So what does that actually create? Well, labels is essentially an index position referring to a particular cluster center, which is an RGB code. And when you pass in those labels into RGB code, so it's saying, okay, grab the first row at index 0, again, grab it again, and then we'll do that same for the other rows, that if you run this, you essentially now get the kind of averaged out RGB values. So now these are all the same. And if you take a look at your original values here, in fact, let's just go ahead and show it since we don't have it displayed yet. If we say image as array 2D, what it's doing is it's essentially reassigning all these points here to be closer to whatever their cluster center is. So it's just reassigning those points and those colors to now go straight to the color center color. And this is just using indexing. So labels are the index positions, and then we're passing it into RGB color codes to actually get those center values. And then what I can do is the following. I can say NumPy reshape, and I need to reshape this back into a 3-dimensional object so I can display it. So reshape this as height, width, color channel. And now I'm going to pass that in. So right now, RGB codes labels, this is the image 2D array version. I'm going to reshape it so it's 3 dimensions, essentially making all these red values be in a 2D array, all these green values be in its own 2D array, and then all these blue values be in its own 2D array. So it's going to break up again back into different color channels. And this is now my quantized image. So I'm going to say this is my quantized image. Run that, and let's go ahead and check out the quantized image. So we check out our quantized image, and notice all 3 of these values are now the same. And this is analogous to our original image as array, where it's essentially kind of averaging out all these points to go to their cluster center. What does this actually look like if we were to display it? Well, we can say plt imshow, run that, and this is your quantized image. Recall we said k is equal to 6, so we should see just 6 colors. And do we? Well, notice I see a dark blue, so that's 1, a light blue, that's 2, light orange, that's 3, dark orange, that's 4, this gray, that's 5, and then everything else is actually the exact same color. It's black, maybe with a little bit of that same gray, but those are essentially the 6 colors. There's kind of 2 blues, 2 oranges, and then 1 gray and 1 black for a total of 6 colors. And you can definitely play around with this to see how else you can kind of quantize these colors. Okay, that's pretty much it for color quantization of k-means. I'll see you at the next lecture.